Today we are going to discuss on the bendy moment diagram and probably the shear force diagrams, right? So, so the fundamental concepts, right? So you need to know is does so first thing is you need to know how you idealize a beam in the real world to the analytical world, right? So from the real world, we bring down to the analytical model. So with this, we should have some idealization, right? How a particular object in three-dimensional, maybe two-dimensional, is going to be idealized, right? So first we need to know the important concept is degrees of freedom. So we will talk about this a bit. What is degrees of freedom, right? So the degrees of freedom is the number of available, let's say the translation or the rotation at a particular, let's say if a beam, it's a joint, right? So if you consider, let's say an object in three-dimensional space, right? An object in three-dimensional space. So you can see, right, in the next, yes, you can see here it can go in translate in x direction linear translation or linear translation in y direction and the linear translation z direction, as well as it can rotate about x. This is the x-axis. It can rotate about x and it can rotate about y and it can rotate about z. So that means uh, an object in three-dimensional space have 6 degrees of freedom, right? 3 linear translation and 3 rotations, all in the linear translation in x direction. Again, I'm showing this in x direction, y direction, z direction, and rotation about x, rotation about y, and rotation about z. So, but we are actually talking at the two-dimensional level, right? So that means we will probably be working on one plane, right? So that we are not going to worry on the z axis, right? So we will be working on xy plane. In that case, it cannot translate in z direction, right? And it cannot rotate about. Can you see if a particular object is rotated at time to time, that will have different z coordinates, right? Say, let's say here, then, right? Can you see different z coordinates? Here also different z coordinates. The height is changing, but here height is constant, right? It rotates about z, right? So that means we cannot use these as well for 3D two-dimensional case. So that means we will be only dealing with translation in x, translation in y, and the rotation about z axis when we are going to two-dimensional plane. So can you see? This is the idealization. You have now 3D object was there. Now this is a 2D object. So you can translate in x, translate in y, and translate in he said, so these three are the same as the figure shown in below. This is the perspective view, so they have only just displayed the uh, plane arrangement, right? So these are your degrees of freedom available for a two-dimensional case, right? So basically in structural analysis as well, we fundamentally works with uh, two-dimensional case, right? So we already have 3 degrees of freedom. So degrees of freedom means a single direction where a node is permitted to rotate or translate, right? So simple as that. And if we go with, there are several kind of supports, right? So first thing is we have fixed supports. So fixed means this part of the beam is fixed to this support, right? So that means it cannot, let's say this is our coordinate system. So you saw x, y translation and rotation about the z axis you cannot see because it's into the paper. Okay, it's like this: x, y, z. Okay, so if I call it like this, so since it is fixed, think about this joint, right? It cannot go in this direction, right? It is restrained. So that means this degree of freedom in x direction is not allowed. Okay, so it cannot also go in y direction as well, right? So the y direction, either up or down, that degrees of freedom is also restricted, right? So the other thing is the rotation about z axis. Since it is fixed, it cannot even rotate as well. So how they would simply restrict this? If you want to restrict something, you have to have some force or so that we call a reaction, right? So that means if you have a resistance to linear translation in x direction, you should have a reaction, right? You should have a reaction probably in this direction, right? In this direction you have to have a reaction, right? Let's call it try to move in this way, and let's try to call it move in this way. So it needs to have a reaction. So that means a resistance, right? So if it is trying to bend this way and it stops it, right? So that means it should generate a resistive movement, right? That's why we have 3 reactions at a fixed support. So that is 2 translation forces, and two vertical and horizontal reactions, and the bending moment. So here the degrees of freedom are actually 0. Here reactions equal to 3. But when it comes to a pin support, right? If it is a pin support, still pin support is in good contact with the ground, right? So pin means it will not allow the beam to this. Think about this node. This beam cannot translate in this way, right? Because the support is attached to the ground, right? And as long as well as it cannot go in y direction as well. So these degrees of freedoms are restricted. So this is cross mark, okay? It is not allowed. But think about the rotation. It is not restricted, right? So if this beam is loaded, so it can rotate like this, right? But here, if it is even loaded, this part, the closer to the support, is not rotated, so it will remain as it is, but with towards the middle of the beam it will deform, right? But at these points rotation is zero. There will be a moment generated at the support, right? So here at the support also it will rotate, right? So that means it does not have any resistance to a rotation, right? So probably you will ended up with it cannot go in x direction, so that's how a reaction is generated in horizontal direction, and it cannot go, it try to move in y direction, but there's a reaction the support is giving, but it does not give any bend, any resistance to bending. So that means you have reactions equals to 2 and degrees of freedom to 1. Can you see? Initially we had degrees of freedoms 3 for 2D case, right? So that means a fixed support will restrain all of these 3. How? They generate 3 reactions, right? The pin support will restrain 2 degrees of freedom, so that it will have 2 reaction and 1 degrees of freedom is remaining, that is rotation, right? If you consider a pin support, right, so it is on the ground, so it will not let it move in this way, right, or this way, right? But it can move in this direction, right? So, and as well as if it is loaded, it can rotate as well, right? It can go in this way. That's a roller, right? So the only restriction is the translation in y direction, right? So that you will ended up with a reaction in y direction only, right? So reaction equal to 1. The degrees of freedom available, this is the degree, these are the degrees of freedoms available. So can you see there's a relation, right? Summation of these two always a constant, right? At a joint, degrees of freedom 0, reactions 3. 2 degrees of freedoms restraint, so that means there should be 2 reactions. So the reaction should be there to restrain that degrees of freedom. That's simple as it is, right? So one will be left at a pin support, so that is the bending moment, right? It can rotate, so that means it does not provide any restriction to bending or rotation. and the roller support, it does not provide any restriction to even rotation or the translation in x direction, so that it will only constrict 1 degrees of freedom and 2 will be remaining. This is the remaining. Okay, these are the remaining degrees of freedoms, right? So the restrained degrees of freedom will have a reaction, right? So the remaining degrees of freedom plus the number of reactions equals to 3 in the case of two-dimensional joint, right? So yes, you can see this still from here, right? Can you see a fair representation of fixed beam, right? So it cannot actually, can you see? Here, think about this joint, right? It cannot actually, so if your beam is rotated, right? Here, actually no rotation, right? So that means that part is totally restrained, right? So this is the real world, right? Can you see it's bolted, plates are there, right? It cannot go in this way. Think about the x direction is this, think about y direction is this, is a this, sorry, y direction is this, is a this, like that. And yes, you can take xyz in any direction, right? But usually we use x direction in the longitudinal axis, right? So this is only an analytical approximation, right? You can see it cannot go in this way or this way, and it is restricted. So actually this beam is in 3D, right? So it can either rotate in this axis or rotate about this axis, right? So anyway it is fixed, right? But think about only one plane, right? Since we are working in two-dimensional, okay? If you get the concept of two-dimensional, you will be getting this for even a 3D very easily, right? So it's just like that, and it is rotated. It cannot move in this way or this way, and it cannot rotate about this, right? Rotation is restricted. So that means at the base you will have a bending moment generated and two reactions as well, right? As he draws, right? So this is a pin case, right? Can you see here? There's a rotation, right? It is not restricted, right? So these are the actual pin jointed in real life, right? So only have two reactions. It cannot restrain the rotation. So this is a roller support, right? So it will only have one reaction, right? So now we are moving to, yes. So let's consider a simple beam, right? Suppose there's a pin load at here. Let's call this distance L, and this distance is L by 2. Okay. So this is a pin support, right? If it is a pin support, you know, only reaction you will have is in this way. Sorry, I will draw it in another color. This way, and this way, this way, this way, right? But so these are the unknown reactions, right? We don't know the value of these forces. Let's say this is P, right? So if you consider the system, right? If you consider the system, the available number of reactions, right? Available number, the reaction in horizontal direction is only these two, but this beam does not have any horizontal loading. So then these forces will be actually how much? Zero, because the beam does not have any horizontal loading, right? So there's nothing left to frustrate, right? So that means this becomes unknown to known forces, that is zero, right? Right. So we will be only remaining with these reaction. Let's call it V1 and V2. So since we know this is symmetric, right? This is symmetric. So what we know is V1 should be equal to V2, right? So we can consider V1 is equal to V2. We can notate it as V, right? So you have, so you have 3 degrees of freedoms, right? So if you rotate here for a system as a 2D, so that means you have 3 equations as well. The summation of forces in x direction, summation of forces in x direction, summation of forces in y direction, and bending moments summation about the z axis, right? This is Fy, Fx, right? So these are the available number of equation for the whole system and at a joint, right? So you can write like this, right? So if you consider the system, right? So the available number of reactions are V1 and V2, right? So we'll consider upward forces are positive, right? So that means, so we know V1 and V2 equals to V, right? V plus V. P is in negative direction, 0. We know the summation of forces in y direction is 0 if it is in equilibrium, right? So V is P over 2, right? So now we going. So if it is loaded, actually, this will bend like this, right? So we need to know what is the bending moment in this member, right? So we know at the joints there are no restriction to the bending moment, right? No restriction to the bending moment. So that means support cannot restrain any bending moment, right? But think about now the beam. Beam is deflected like this. So there are internally bending moments generated, and due to that shear forces are also generated, right? For this kind of loading, right? So we need to know that bending moment. So at the end, they are going to transfer it to the support. That's the transferring mechanism. So probably even if it is have a shear force, it can transfer it to this support, right? Because it can take shear, but it cannot transfer bending moment to this support. Why? Because the pin supports doesn't provide any reaction to bending moment, right? So it just like you keep something on thing. You prevent its translation, but it can rotate like this when you load it, right? So now we are going to determine the internal bending moments, right? Along this beam, right? How it is bended, going to bend it, right? So for that, we need to know these shapes, right? So this is called sagging. This is called hogging. The shapes, okay, and sagging. So we usually call hogging moments are positive and sagging moments are negative, right? So think about this position, right? So what they actually does is, if you cut this beam from here, right? You cut this beam from here, you will have, compared to this location, this part is going to move in this way, and this part is going to move in this way, right? But if you cut here, this part is going to move in this way, right? So this is the hogging moments, right? So if you draw it more generally, right? If you have a beam section, so to make it hogging, you should apply a moment like this, right? To call it sagging, you should apply a moment like this. Always see the right end, it is clockwise. Always see the left end, it is anti-clockwise. Can you see the right end? This is the right end. If you consider this part, this is the right end, right? So it is clockwise. If you call, so it left end, it is anti-clockwise, right? If you see the right end, it is anti-clockwise. If you call this left end, that is anti-clockwise. So we can determine it in only using one end, right? So we can take for the clockwise moments are positive and draw this one. Don't be confused this anti-clockwise, right? So we are going to at the end to determine, because we are taking only the left end, right? So the right end, right? So right end, and see at the right end, if you ended up with a positive moment, that is a clockwise, that means hogging. If you end up with let's say negative, that means anti-clockwise, that is sagging, right? So yes, we can go ahead, and yes, we can go ahead and cut this beam, right? So we have a point load here. So this system has a point load in middle of the beam, right? So until the middle of the beam is kind of uniform and there's no loading, right? So the bending moment I can determine in this region, and after that loading also I can determine from this region. I use a common equation and then substitute the value. So I'm going to cut from here, right? I'm going to cut from here. So you know this is P by 2, right? So there's the reaction P by 2, right? Always. So you are going to do it in clockwise positive, right? So apply a clockwise. Don't apply it here. You will be confused again. If you apply like this, you cannot simply determine whether it is sagging or hogging. It looks like sagging, right? But it's actually coming this way. And again, always draw it across the member, right? So this is, let's say this is M, since we don't know the value, right? So, and for shear, always remember left up, right down, right? So if it is the left end of the beam, it is up. If it is the right end of the beam, left up, right down, right? So this is the right end of the beam. Sorry, yes, this is the right end of the beam. This is the left end of the beam. This portion, right? So here it is left up, right. This is again left up, right, down, right. So we are going to draw, because if you cut there, right, there will be a moment and a force. We call it shear force, right? Left up, right, down. We call it shear force. So I'll apply that shear, right? So I can write the equations for this part, right? If the whole system is in equilibrium, this part should be in equilibrium as well. So you can write moment equations about this position, right? Let's call this A. Let's call this X, right? So here X is less than L over 2, right? So I can write the bending moment about X, right? So the S is not coming. M is clockwise positive plus P over 2 into this distance X, right? Cut from X. Yeah, so X, here the X is less than L by 2. Here the X is greater than L by 2, right? Equals to 0, right? So M is minus Px over 2, right? So if you apply any value, right? If you apply any value, so you can see your M is negative, right? So negative means it is getting an anti-clockwise bending moment. So at the right end. So what does that mean? It is actually a sagging bending moment, right? So yes, it's correct. If you load apply like this, it is sagging, right? Entirely throughout. So maximum bending moment. So you can see this is valid until X is getting L by X is reaching L by 2. So that means the negative, so X M is proportional to X. So that means if X increases, this value increases. So you can apply until L over 2. So the maximum value would be when X is equal to L by 2. So that means PL over 4, right? So this is a straight line, right? So the bending moment Px over 2, right? So it's like this, right? After X by 2, right? You can determine again from this E. So you need to write another equation because there's a point load here active, right? So your equation should change, right? Let's consider that as well. And we would cut here, right? That's a point load. P over 2 P, right? Here it's X. So one thing, you can write the summation of forces in y direction as well. So that is S is equal to, so actually S minus, sorry, P minus P over 2 minus S is equal to 0. That is S is equal to S is equal to P by 2, right? So this is a shear, right? So you can see there's a uniform shear, right? Until there, it's the shear force does not change with X, right? So that means here it's a constant shear, right? So no load applied, right? So once the load applied, right, you can see again we are going to have a cut here. I call this M, and this is the right end of the part, right? So write down S. So I can write summation of forces in y direction, P by 2 minus P minus S equals to 0. So I'm getting with minus P over 2 is equals to S. So that means negative shear, right? So shear is in the other direction, right? So that means shear is not in downward, shear is in upward direction now, right? Okay, so you go there and you can write down like this. So for the bending moment, you can write it's about X, right? So moment about X equal to M plus P by 2 over X, P by 2 into X. This P into X is in anti-clockwise direction. This is in clockwise direction about this point, right? So this distance is X minus L by 2. Is equal to 0, right? So you can simplify. This is PL by 2 minus PX by 2, right? So that is M is equal to P over 2 X minus L, right? So you can see the other part. So the first half of the bending moment diagram was okay, right? So the second part at L by 2, right? It is again PL over 4. It should be continuous, right? It should be continuous bending moment diagram here for this case. And if it is X equals to L, it is 0, right? So you can simply, so this is your shear force diagram, right? So that is entirely negative, right? So what does that mean? So this is a sagging bending moment, right? So we'll consider something like this, right? So let's say, so the one thing, don't worry if you have some load in like this, right? A triangular load, right? It's W, right? Let's say for L distance, right? So one thing is you need to write down the intensity of this load because it is changing with x. So for L distance, if it is W, what it would be for an x distance. So that would be give you the intensity is Wx over L, right? If you cut it from here, right? If you cut it from here, let's say you have x distance, right? So you know the load here is, so if it is x naught, it is Wx naught over L, right? So what is the total force? Total force is total area of this, right? So nothing is going to be complex, right? So it's triangle half into Wx naught over L into x naught, right? So the bending moment is, right, the total load. Bending moment is the distance to centroid from about this point. If you take moment about this point, right? So it is a triangle. So you will have 2/3 of x naught, right? So this is the x bar. So if you have a triangular, don't be confused. The thing you have to do is, how do I take this intensity in analytically? So that means, how do I take this using a mathematical formulation, right? So everything civil engineering deal with, so they take the real world into the analytical problem, right? So that means they formulate everything using mathematics, right? So we will go with uh, this problem. The beam is like this, right? It's a straight beam. So have you noticed there's only 3 equation for you to solve in 2D case, but that means if you have uh, supports which generate 4 or 5 reactions greater than 3, that is indeterminate, right? You cannot solve for that, right? Here only two reactions, you can still solve for that, right? You can still solve for this, right? But if it is the number of reaction is uh, larger than the number of available equations, 2D case, it is an indeterminate, right? Until that, it is determinate, but it cannot be less than the number of available equations, so that it not be a structure, it is an unstable, right? It is unstable. So here, there's a special case, right? Support A. So you can determine if this is, let's say, a pin support, and a roller. So this, since there is no horizontal loading, you can approximate the horizontal reactions are 0, right? Horizontal reactions are 0. So it will only have vertical reaction as well, similar to a roller support, right? If there are no horizontal loading, you can see the working principle of a roller support is exactly equal to a pin support, right? There are 3 available 3 reactions, right? But you, how much you have? 3 equations. But can you use all three? No, because your horizontal loading is 0. So that means you cannot use horizontal equation as well. In that case, you can only have 2 equations. So 2 equations, 3 unknowns. You can't solve this. But here you have a hinge there. Okay. So if there's a hinge means the simplest thing is you idealize a door hinge, right? This is the top view, the door. This is the wall. So look, I'm looking at the top. Okay. So door cannot move like this or move like this, but it can rotate, right? It can rotate. If a load is applied like this, that means there's a resistance to shear is there, right? Shear resistance at a hinge is available, but it can rotate individually, right? Right. So it can rotate. So that means if it allowed to rotate, what will be the bending moment? 0 at a hinge. So we know the value of bending moment is 0. So that means there's an additional equation we can generate, right? So that means it is going to become, it is going to be determinate, right? It is going to be determinate, right? There's a hinge. So we will apply a load like this, right? So let's call it 1 kilonewton per meter, right? So we will apply 4 kilonewtons here. There's a hinge here. Let's call this C, right? Here it's B, here it is A and D, right? So the supports, 3 supports are there still, right? This is an internal hinge, okay? So you have RA reaction, RD, right? So you can solve this at the first place using the hinge. So you know about the hinge. There's you can rotate, the 2 beams can rotate relatively, right? So that means bending moment is 0. So that means you can take bending moments about this, since you already know the moment is 0. For each case you can take the bending moment. So for each beam you can separate it and take the bending moment, right? This is RD. Okay. So now this is right end. Okay. So if I apply it clockwise, so this would be sagging, right? So sorry, this is the left end. Okay. This is the left end. Okay. If I need to add, if I stick to my sign convention, okay. If I stick to my sign convention, this is should be other direction because hogging positive, right? Hogging positive, and this is the left end of the beam. So shear is left up, right down, right? So if it is M, right? So I can write equations and draw how. So the M is 0 because the bending moment above the hinge is 0, right? So you can just equate the total bending moment M, right? Right? It's 0, but we just write it and set it 0. So this is total W is 1 into this length. So this length is 4 meters. This length is 2 meters. This length is 4 meters. And this length is 2 meters, right? So this length is 4 meters. The total load is 1 kilonewton per meter into 4 meters. So that's 4, right? 1 into 4, the load per unit length divided by multiplied by the length, right? So that load, so this is a moment, okay? So acting at the middle of this part, right? So probably the lever arm, the distance to action of the load is 2 meters, right? So this should be in the other way, right? Anti-clockwise, this is clockwise. If I'm taking anti-clockwise, oh, so I will take anti-clockwise negative, so that means clockwise positive. Here it is anti-clockwise, the load acting in the clockwise direction, and again the R is anti-clockwise, RT into 4 about this point. RD have 4 about this point, right? There's no hinge here. So you can take M is 0, RD is 2, right? 2 kilonewton. So it's positive, and that means the direction is correct, right? It's in the upward direction, right? So the second way, right? So we are going to draw, yes, we need to first determine the other reactions as well. So we already know the RA plus RB plus RD is equal to total load, right? So total load is 1 into 4 plus 4. The total load is so sigma F in vertical direction, right? So it is RA plus RD plus 2. Four plus 1 into 4, right? So this is either horizontal loads equal to horizontal upward, vertical upward loads is equal to vertical downward forces, right? So you can write this is 2, right? So RB plus RD, RA is equal to 2 minus 4 minus 2, 2 plus 4 is 6 kilonewtons, right? So you can just, the easiest way to take C is you can take moments about B for this part, or else you can take from the hinge, because if you take from the hinge you need to draw this reaction as well. So if you take it from the hinge, that's easy, right? So RB into 2 plus RA into 6 equals to 4 into 2, right? About hinge on this part. So you know the hinge is, the bending moment is 0, right? So you can write RA, it's clockwise into 6, right? Yes. RB as well clockwise into 2 equal to 4 into 4. It's anti-clockwise, right? So yes, 6. So you know RB is 6 minus RA. You can substitute that. So here 12 minus 2RA is equals to 8. So here it's going to be how much? So RA, it's going to be 6. So this is 16, right? So 12 is cancelling. This would be 4, and this would be 4RA. So RA would be 1 kilonewton, and RB is 6 minus 1 is 5 kilonewtons, right? So the first thing is, you can go ahead and write down equations. So for this, you have to consider several regions, right? Because first region is this region, right? Up to the point load. So then you have another support, right? So this is the second region, right? X, this is x less than 2. If it is x distance, x less than 2. This is x greater than 2 and less than 4, right? So this is up to hinge, right? X is greater than 4 but less than 6. X is measured from this end, right? Right. So this is X is in between 6 to how much? 10, right? 6 to 10, because this load will be acting uniformly through until the end. So these are our regions, right? Within this region, no any loads can be seen, right? Can you see? Right. So the first region between 0 to x. So I will draw that beam. So RB is 4. Sorry, it's 2. Hinge is there. It is 1 kilonewton per meter, right? So here it's 5. Here it's 1, right? Here it's 4, 2, 2, 2, and 4, right? So X is measured from this end, right? So first I'm going to cut it from here. So I can write m clockwise, left up, right down. I can write the equation vertical. I will take only vertical one and s will be there. So s is equal to directly 1, right? And m clockwise plus 1 into x is equal to 0. You are taking about moment of at this point, so s is not coming, right? So m is minus x. So from that moment you can see, if you plug x values positive, so minus m would be minus. So what does that mean? That's going to be sagging, bending moments, right? So in this region, right? So then I'm going to cut it from here, right? So if I cut it from here, so m, it's s, right? Now my m is, I can vertical sum. So this is from the vertical summation of forces, right? 1 minus s is equal to 0. That's how s equals to 1, right? So yes, this is from x from 0 to 2, right? This is 2 to 4, right? 2 to 4, right? So yes, you can go ahead and write still, if you take vertical force equilibrium, so now you don't have a cut here, okay? You don't have a cut here, you have the cut only here, right? So you have s1, still s1 and 4, right? So if you write it, 1 sigma in vertical direction plus 1 minus 4 minus s equals to 0. So s is minus 3. Shear is minus 3. So shear is 1, right? Let's see. So bending moment. So m is, so m plus, so now actually I will erase this, otherwise you will be confused with this. Okay. So m plus minus 4 into, this is the x distance now. Okay. So x minus 2, right? Minus 4 into x minus 2, and then 1 into x, right? That's clockwise direction. 1 into x, right? So that's it, right? That's it. Yeah. So that's going to be m is equal to 3x minus 8. So this is summation of moment is 0. M is equal to 3x over 8, right? So here, then I'm going to cut it from between right? Cut it from here. Here the x is greater than 4, less than how much? 6, right? So you can write, so m here, left up, right down, right? Right end of that part is here. So here is like this. So you can write vertical summation of forces, right? Is 0, right? So 1 minus 4 plus 5. 1 minus 4 plus 5 minus s equals to 0. So s means how much? 2, right? S is equal to 2 for this within this region. Within this region, s is 1. Within this region, s is 0. So you can see in those three regions, shear is uniform, right? Not depend on x. Just keep in mind, but the bending moment depend on x, right? So the first thing we are going to do, then take the bending moments as well. So moments about this location for this part. So m clockwise. So this 5, this is 5, right? So 5 into, so now this is x minus 4 plus 4 into x minus 2 minus, that is anti-clockwise, plus 1 into x, that is clockwise, equals to 0. Is that right? Yes, right. It's correct. So this positive, m is equal to minus 2x plus 12, right? So minus 2x plus 12, right? So then you will be going to, so this part is done. Now we are going to the final part, right here. So the x would be like this. This is before the hinge, right? This is before the hinge. This is after the hinge, right? This is going to be x, okay? So this is going to be x, and left twice, right down, right? Okay, so here, one thing you can notice is, right? So it's, there are several things, right? Hinge and force and other things. But what if you consider this part? That's pretty easy, right? So it is, again, this is Hawking positive, right? For the left end, it's anti-clockwise, and right down, left up, right? So there's only this uniform loading and a load of how much? 2. Right. So you can easily write, right? Both these are S. So you can write S plus 1 into, right? So the total length is 10, right? Still X is written from this end, right? X is measured from this, okay? Don't forget that. So this is 10 minus X, right? This is 10 minus X, right? So S, so that is acting on the downward side. So either you can write 5 minus 1 into 10 minus X plus 2 is 0, right? This is S. So the S would be how much? 8 minus X. So can you see now X depend on, sorry, S depend on the X, right? So that means shear would be a function of X length up in this region, within this region, right? So this is X is in between 10 and 6, right? For bending moment, you can write, so you can write like this, right? So for here, whatever happens, we consider hogging positive, right? So need to hogging, for hogging, if you consider this end, you should take clockwise moments, right? Now you are taking the other end. You are not taking the right end. You are taking the left end. So that means you should consider anti-clockwise, right? If you consider anti-clockwise, this M is positive. Okay, so you are taking moments about this position. So S would not come, right? M is anti-clockwise and 2 is also anti-clockwise. 2 into 10 minus how much? X, right? And W is 1, right? So that is clockwise, right? So then it would become negative, right? Okay. 10 minus X is the total load. And you have to multiply it by the lever arm. 10 minus X over 2. Right? So this would become is equal to 2 plus, so this is the total load. This is the lever arm, that is also 10 by X over 2, right? Whatever acting, there's be L over 2 for that pendulum, since that is uniform rectangular load, right? So this bending moment would be like this, right? So now our regions are okay, and you can go ahead and draw the diagrams, right? So first thing is, did you remember this one? So here, if you consider the clockwise, right? So we took hogging moments positive, right? You remember hogging, right? If it is for right end, that is clockwise, left end anti-clockwise, right? So since we already usually cut it from the right here and take the right end, that's why we consider clockwise positive, right? That's why we take clockwise equations. But here you are taking anti-clockwise, so take anti-clockwise positive. At the end, it is going to be also a hogging moment, right? That's what matters, not the anti-clockwise or clockwise. It should be a hogging moment. To be a hogging moment, If it is right end, that's clockwise. If it is left end, it is anti-clockwise, right? So yes, you can go ahead and draw the diagrams and the bending moment, right? So the regions are x equal to 2, 4, and then 6, and then 10, right? So this shear force diagram, right? So shear, you remember, you can take that load, right? So S equals to 1, right? So that means if you are at here, you have a load upward, so that means positive shear of 1. So that remains unchanged until 2, right? At 2, you have 4 kilonewton downward. So that means you have to go down by 4. So this is 1. 1 minus 4 is minus 3, right? So that remains unchanged. You have to go until 4. That's why you got S is equals to minus 3, right? So then you have 5, right? So you are at minus 3, you have suddenly plus 5. So you have to go up by plus 5. So that this should be altogether plus 2, right? So that remains unchanged until you go here, right? And then, right? And then your shear force is 8 minus x, right? At x is equals to 6, it is 2, right? 8 minus 6 is 2. So that means you are at here, right? So when x is increasing, right? X is increasing gradually. So that means it is going, the bending moment 8 minus x would decrease, right? Look like this. At x is equals to 10, it would be minus 2, right? When you came to minus 2, right? When you came to minus 2, you have a 2 kilonewton reaction upwards. So you should go and meet the beam. So the first criteria, you should start from the beam and you go upward and downward and upward shear, positive shear, and go. And finally, you should meet again the beam, right? This is the total shear force diagram. So within these methods, it's very easy. So if you have a point load, there's a sudden change in shear, right? But not change in shear if you don't have any load within the beam, right? But if you have gradually a loading, so that means collection of point loads. So collection of sudden changes, right? So gradually changing, and again, this would look like this, right? So how about the bending moment diagram? So you can draw that as well. Right? So I need to erase this. Right? 0, 2, 4, 6, and 10. Right? Within x equals 0 to 2, our bending moment was minus x. Right? At it is minus x. Here it is 3x minus 8. In this region, it is 3x minus 8. In this region, it is minus 2x plus 12. In this region, it is minus 10, 2 into 10 minus 6. 10 minus x plus squared over 2, right? So if x is equal to 0, so you can just plot the end values, right? So this is the total bending moment diagram, right? So x is equal to 0, your bending moment is 0, right? X is minus 2, so you plug, sorry, x is 2, you plug x here, it's minus 2, right? Minus 2. When you plug, so in this region as well, you should, if you plug 2 into 3 is 6, 6 minus 8 is minus 2. So that should be continuous, right? The right hand side of the right hand boundary and the left hand boundary should be equal. That is continuous, right? At x is equal to 4, right? 4 into 3 means 12 minus 4 is, it is plus 4, right? It is plus 4. Look like this, right? Right? So it is plus 4, right? And here also x is equal to 4. 4 into 2 is minus 8 plus 12, right? Minus 8 plus 12 is again plus 4. That is continuous, right? So left hand, right hand is equal, right? So at x is equal to 6, 6 into 2 at here. Can you see at the hinge, what is the bending moment? 6 means 6 into 2 means minus 12 plus 12. It is 0, right? So as we expected, at the hinge, the bending moment is 0, right? So at x is equal to 10, right? X is equal to 10, bending moment is 0. Does that mean it is a straight line? No, right? It is a curve, right? So probably you can take where it would be a maximum, right? So you can take like this. So your bending moment is like this. So you can take dm over dx, right? Since the load is acting downward, so probably you will have a sagging bending moment. So because this beam is going to sag, not like up, not like this. Due to this load, it is going to sag, right? So that's obvious. So that means the bending moment value should be negative in this region, right? But you need to know what is the maximum value, since it is a curve, right? Curve, if you, so to draw a curve, the fundamental is you need to at least know 3 points. You know the edge points, right? So I will find the where I get the maximum, right? So the dm over dx is here it's going to be 2x, that means x2, right? So here it's going to be 2 into 10 minus x over 2 into minus 1, right? 2 into 2 cancelling. So it's going to be 2 equals to 10 minus x. So if dm over dx equals to 0, right? So minus 10 over x equals, so x is equal to 8, right? When x is equal to 8, this will be a maximum or minimum. In this case, it should be minimum because it is should be negative, right? Because it is sagging. If x is equal to 8, so just plug the value. So this is going to be 2, right? This is going to be 2, right? So this is if x is 2 at x equals 8, m is, this is 2, this is 2, 2 squared 4, 4 over 2 is 2 plus 2 into minus 2, minus 4. So that would give you minus 2, right? X equals 8, it is minus 2. So now you can draw the shape, right? Can you see these are y equals mx, right? Y equals mx plus c or whatever. So that would give you a straight line like this, right? A straight line like this. A straight line like this till this, but here it's a curve, right? So you need to draw that curve. So this is your final bending moment diagram. So you can see, right? It's adhering to our fundamentals. Here it is negative, right? Bending moment diagram entirely negative. So what would that mean? It is sagging, right? About this part, we cannot say because it's a support is here, right? We cannot really say if it is sagging or hogging even for a beginner, but you can see from this one, it is positive, right? So in this part, you have hogging moments, right? Hogging bending moments. So this is the complete fundamental, right? So if you follow this, anything would be possible, right? Thank you.